Okay, guys, so in this video, we're going to be starting our discussion on sequences and series. So we did that activity in Desmos the other day. So now we're going to really get into how do we figure out these sequences? How do we define them? How do we come up with rules for them? How do we find parts of them? And the series, how do we find the summation of those different patterns and sequences that were given? Okay. So first thing is we got to know, well, what is a sequence? I'm going to move myself up here a little bit. So a sequence is just an ordered list of numbers. It could be in any order. It could be any set of numbers. We have what are called finite and infinite sequences. So finite means there's an end to it. So it's going to go from the first term to the fifth term, or the third term to the eighth term, right? There's a set amount of those terms. An infinite one is exactly how it sounds. There is an infinite amount of terms. It's going to keep going on and on and on. And the way that we tend to show that is with these things we call ellipses. And you've seen them before, right? They're this dots over here. It just means that's continuing on and on and on forever. Okay. So that would be a denotion of infinite. That's going to be your clear set way of knowing that I have an infinite amount of solutions. We do have domains and ranges of these sequences. The domain is each term. So we have term 1, term 2, term 3. It's basically the position that it's in. And then the range is the term itself, whatever it is actually. I'm going to move myself back down here. So unless told otherwise, we are starting our domain at term 1. So it'll always be first position. And the reason I bring this up is some people are visually going to want to have this table here in order to help us out when we have to write the rules for these sequences later on. Okay. Again, determining whether it's infinite or finite, again, depends on how many there are. And the last thing down here is we're going to be able to write rules for these sequences. So the rules are going to be in terms of n. N is our position. So both of these rules, whether it's 2, 4, 6, 8, you see it's a truncated sequence. There's only 4 terms there. 3, 5, 7, 9 ends. Or whether I have 2, 4, 6, 8 ... or 3, 5, 7, 9 ... meaning it's going on forever. Both of those rules are 2n. 2 times n. 2 times the term position gets me that value, right? So in this case, I can see they're increasing by 2 each time, 2 to 4, 4 to 6, 6 to 8. I'm going up, I'm adding 2 each time. So I can also think of it as a linear function in this case, and we're going to learn later on how some will be related to linear and some are going to be related to exponential functions to make our life easier when we have to come up with these rules. Okay, so 2 times the n position does in fact get me these values. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. So it does in fact get me those values of the term. Okay, so here's just some examples on how we write them from a rule. So if they tell you, here's a rule of your sequence, right? I can come up with the first however many terms. I can make a table if I need to. It just depends on what the situation is calling for. So I can see 2 times n plus 5. So to find the first number, I plug a 1 in. That's 7. Plug a second number in. I put a 2 and I get 9. Put a 3 and I get 11. So forth and so on. I can do the same thing over here. Just make sure you're plugging it into the exponent spot in this case. All right. And these purple and blue 2s and 3s are to just show you the pattern that's happening, right? Each of my final terms is increasing by 2, right? 7 to 9 is 2. 9 to 11 is 2. 11 to 13 is 2. That is a linear function. And in fact, that 2 is actually in the exact same position as the slope, if we want to consider it a slope, of this given function, 2 times n plus 5. That's kind of like y equals mx plus b. So the fact that these 2's all relate to the 2 here is not a coincidence. Okay, so adding and subtracting shows a linear pattern. Multiplication we have on the other side, right? Times 3, all of these. Well, that happens to be the base of my exponential problem. So multiplying or dividing is going to be related to a exponent problem. Okay. And down here, we're going to talk in terms of adding and multiplying. That's why you see those words highlighted. Everything is always going to be in terms of addition. So if it's really a subtraction we see, we're going to say it's plus a negative number. If we see a division, then it's going to be times the reciprocal, because the division is just the reciprocal of multiplication. So that's really important to note, that we are going to talk things always in terms of the addition or the multiplication. Addition is always linear. Multiplication is always going to be exponential. Think about it, it's repeated multiplication. That's a power. Okay. We're going to go through in class some examples of these, finding the different terms. But again, all we're simply doing is plugging in the value here. And this is a typo. That should be, oops, that should have been a to the n, not a sub a there in the first one. But we'll fix it when we go over these problems in class. Okay, coming up with the rules of our sequences. So we're always going to want to know, how does the number itself relate to the position that it is in the sequence? So for example, question number letter A, I should say. Notice, actually all of them, notice I wrote n and then 1, 2, 3, 4, and 1, 2, 3, 4, and 1, 2, 3, 4, because I'm making note of where those numbers are, so I can use that when I write my rules, because the rules are always going to be something with an n involved. So in this case, I noticed, well, I have negatives, so it's definitely going to have a negative there, right? And then I kind of took a look at, well, how could I relate these numbers in some way, shape, or form, right? If I look at addition, -1 to -8, well, that's adding a -7, but that doesn't get me to the next term. So definitely not happening there. There's not a multiplication. 1 times 8 is 8, but 8 times nothing is 27. So still nothing helping me out here. So your next bet is to look at powers. And I'll tell you that right off the bat. You look at squares, cubes, fourth powers, see if anything relates, right? So here, 1 doesn't really help me much, I'll be honest. If you have a 1 in the first position, you're not really going to be able to do much. You always will want to look at the second, third, fourth, and so on, because a 1 in a 1 spot, all I know is it's a 1 position and it's a -1. But if I look at the second position, I have a -8. And in powers, I know that 2 to the third power is 8. Okay, that gives me a clue then, right? Then I look at 27. Well, 27 is 3 to the third power. Seems to be common. 64 is 4 to the third power. So with these sequences, it's all really trial and error till you find something that works. So I always start looking, is it an addition? Do they have common addition? Do they have common multiplication? If that doesn't work, start looking at powers. Look at squares. Is the number a perfect square? If so, great. If not, try a cube. Okay, I found cube. This time it worked. And the fact that they're all negative just tells me that it's a negative of the value cubed, or of the term position cubed. So that's actually how I came up with my rule. It was trial and error, playing around with it. So I'm going to tell you, for the first section, we're going to just kind of be playing with them, but eventually I'm going to give it to you. So it's always addition or always multiplication, or something super duper simple that is like screaming in your face. This is what it is. Okay. But I do want you guys to have that discussion in your head or with each other and talk through to try and find out, what could I use this n? How could I use this n, the position it's in, to multiply, to add, to have a power, to have a sign change, to make it actually appear into this value? Okay. So second one, that's simple. We got an addition, and I said addition, we're going to treat it like linear. So a linear function, most common, y equals mx plus b. Found it, there's my rule. And the second one, I noticed they're all multiples of 2. So a exponential rule, might have forgotten about it, but it's a times b to the x. So your a is your first term. B to the x is your b, your multiplication. And we get our rule 1 times 2 to the n, or just 2 to the n power. Okay. And again, we're going to go through, do a whole bunch of problems practicing this as well. Okay, the last thing, or the next thing, is we're looking at series. So a series is, as I mentioned in the previous one, is the addition of all of the terms in the problem. So again, we can have finite series that end at a specific term. So this says it's going to end at the 4th term, or it might be infinite. Now, if it's infinite, it's going on and on forever. It's never going to end. That means that I can't actually find the technical solution, but I can set up the summation notation. Okay. You still need to write a rule for it. The rule is always coming after your summation sign, just so you're aware. We're going to be using Desmos. You're going to use the Desmos graphing calculator in order for us to come up with these solutions. And I'll show you in class how to do it. But it's basically you type sum, and you'll notice the summation, that big E sigma is going to appear. And then you'll just fill in the values. Okay. Oops. And again, you can see that I went through, I found the rules to see what they would come out to be. And then the summation I set up from 1 to 10. I found out 250 was 10 away. That's the 10th term in there. And then I just put that in the calculator. Came out to 1375. And in the second one, it was an infinite one. I had the dot, dot, dot. So I start at 1. I go to infinity. And I found the rule here. The rule in this case, we see fractions. So n is 1, and I have the fraction 1/2. So it's n over n plus 1. And I can check all of them. They all work out in that case. Okay. And again, we'll go through, we'll practice writing the sum and finding the sum using the calculator.